Well, thank you very much. I appreciate the introduction. Happy to be back at Stanford. I practically never left. I'm going to tell a little bit more about my story. So I've been always involved in one way or the other with a lot of Stanford-related activities. Today, I thought that first I give maybe a quick background about myself and what I did and where I'm coming from, and then talk a bit more about Genapsys and what you're doing there, and open it up to any question that may exist. Making sure that this is good. So at Genapsys, the motto is digitize the world. We're going to come back to it. What's the relevance to digitize the world? Why digitize the world if it's a DNA sequencing company? I'm coming, I was born and raised in Iran, a country in Middle East. Iran and Iraq are neighbors, even though some people couldn't really make a distinction between the two, but they're two different countries. In Iran, I was born in a city called Sirjan, in middle south of Iran. It's a little town with 150,000 people. And the historically is a few thousand years old town or city. The main business of people over there either is pistachio farms or is like a beautiful Persian rocks called kilim or gelim. I was born in a middle-class family. Both of my parents are teachers. My dad was teaching science in middle school, and my mom was an elementary school teacher. After I got my bachelor, I got my high school diploma in math and physics. In Iran, you select, even in high school, if you wanted to study math and physics versus biology versus art. Then I went to Tehran, the capital city. I got a bachelor in electrical engineering from Sharif University of Technology. If you're an electrical engineer here, I'm sure you probably met some other people from Sharif University as well. Then right after that, I did a dual degree in petroleum engineering, which was just a random thing. And then I came to Stanford, getting my master's, both in EE and 2 years later in MSNE, Management Science, and got my PhD in electrical engineering. The last year of PhD, I went to med school. It seemed that I really liked school, but I never finished that. I started company, Genapsys, and that's really the three areas and three places that I've been over the past 15 years. I have three brothers. No sister. All three of my brothers, actually, they did very similar story. They got their master PhD also here at EE at Stanford. One of them, the youngest one, is a postdoc right now here. You probably see him around. The second youngest, which is on the left side, he's working for KLA Tanker. He did his PhD with Marty Fayer in Kingston Lab. And Rahim worked, he's now an engineering research associate at Stanford as well. So he got his master PhD postdoc here as well. So from that standpoint, we've always been around. We've been here at Stanford, and you may see them as the student here. In my past life, I was working on completely different stuff. I was working on radars and signal processing, hardcore signal processing, wireless communication related stuff. Actually, I was part of the wireless network lab in the third floor of Packard building, which was Ahmed Bahai and Andre Goldsmith lab. And there was a very interesting project using a multi-antenna radar imaging system, using multi-antennas, UWB ultra-wideband, to see the signal behind the wall. I was interested in healthcare for very personal reason. A family member of mine, close family member of mine, was misdiagnosed at really young age of 15. And it was very disturbing to watch how broken medicine is. I mean, when coming to semiconductor and when coming to nanotechnology, we're pretty advanced. I mean, these gadgets, the phones that we have, is really a miracle. I said before that if Steve Jobs claimed to be a prophet, I was in his religion. This is really amazing what electrical engineers have achieved over the past 2-3 decades. We can move atoms. We can write IBM with 18 atoms. But if it goes to medicine, we are still in a cave age. You get different type of weird diseases, and just telling you that, hey, you have like cancer. I mean, wait, what? It was not supposed to be. In fact, a dear friend of mine has a cousin the cousin is a serial entrepreneur, very successful, PhD from Carnegie Mellon, computer science, 35 years old. And 2 months ago, 35 years old, 2 months ago got diagnosed with a stage 3 brain tumor. And it's not even the type that you can operate. It's just quite, separated. Basically, it's a thin layer on top of brain. And, imagine that you're like 30 or 35 years old or so on and so forth, and then just telling you that you're stage 3 and you have like a few months to live. We know that great people, in fact, who are contributing a lot, like one of the Stanford EE professors, one of the nicest people that I've ever met when I was at school, got diagnosed with cancer at a very young age. So these type of diseases are really hunting us down, impacting our lives, and we don't really know what's going on. And it was very disturbing to really deal with that concept. Why medicine is still so behind? Why medicine is still in the cave age? So I started learning more about genomics and DNA sequencing. And when you dig in, basically in the world of biology, the highest resolution things that you have is like molecules. Nucleic acids, which is DNA, RNA. Then from RNAs, you're creating proteins. Proteins are the one who's defining the function of the cell. And then you have cells, which is like, bunch of cells creating organs and the rest of these as our body. So majority of these diseases having some sort of genomic cause or a genetic relevance. Different type of cancers. Cancer is DNA disease. Cancer is when the DNA is like, ATCGs is not happening in the right place. Majority of the time in the DNA, but also RNA. We have the same thing also in the protein level. So these are molecules, and these molecules are really teeny tiny. A DNA molecule, like we have about 38 trillion cells in our body. Each cell has DNA. DNA, the whole DNA of a human for each cell is 6.4 billion base pair, ATCGs. And so it's a lot of information. And we all started from one cell, like in a fetus. And that started replicating 1 to 2, 2 to 4, 4 to 16, and so on and so forth. And now we are 38 trillion cells. And every moment of time, we have like, billions of new cells that is really happening. This process, like any other process in the world, is not perfect. So there are errors happening in the process of like replication of one cell to two cell. So you have this DNA in the double helix, as you know, is get single-stranded, and the second strand get built up. This process, with the enzyme that is trying to really build the second DNA, the first enzyme error is 10 to the minus 7. There's a second enzyme coming, trying to clean some errors up, and that's about 10 to the minus 2. So if everything works really perfectly, then you have about 10 to the minus 9 error rate, and of course you have 6.4 10 to the 9 bases, so you get about maybe 6 of them wrong, and depends on where that happens, you might be in a okay shape, and basically life continues, or you're in trouble. And of course, as we grow, this number of, like if you have an error here and another error there, like this is higher chance of you getting to a problem. And that's why with age, we increase the chance of getting diseases like cancers and whatnot. Of course, we can inherit these things from our parents, or it can happen during our lifetime. DNA molecule, each base, ATCGs, are less than a nanometer apart. Of course, it's a 3D structure. So they're really small molecules. With the ATCGs, you want to read them. DNA sequencing is the method of reading that code. That, what is the code basically associated to this one. When I was trying to dig into these, I realized that, okay, well, reading that DNA and RNA code is a very important part of understanding majority of these diseases. The methods that existed for these are mainly optical technologies. So the way that they do it is that, and that's both for optical technologies and other technologies, is called, most of them is called sequencing by synthesis. So how does that work? The same thing that I explained, that like, from one cell we're creating the second, one cell getting to two cells and the DNA get double-stranded. That's the synthesized part of the DNA. They're using the same trick to read the code. So the way that you do it, you have a single-strand DNA that's made of ATCGs. You're injecting ATCG in cycle. You know what you're injecting in, and you're building the second strand next to it. If these nucleotides stick here, and A only stick to T, as you know, and C only stick to G. So if it happens here, and you can somehow detect the reaction, then since you know what you injected in, you know the complementary strand. And that method called sequencing by synthesis, or SBS. Historically, this method, the way that you're trying to detect these ATCGs, is by attaching a fluorophore, a colored tag, to those ATCG, and then doing a multi-stage chemical reactions and using a high-power laser to excite that fluorophore and taking images and finding out the proper frequency for that image and find out if that really got stick here or not, if the reaction happened or not. And that's the method that has been used. It's optical technology and is in a different form factor, but majority of them are the same concept. Those high-power lasers and requirements of a scanner and a robot, etc., make the device really expensive. You're talking about from hundreds of thousands of dollars to $10 million devices, average of $1 million. It also makes it pretty slow. Historically, the first time the method based on for DNA sequencing took 13 years. From 1991 to 2003, $3.8 billion to read one human genome. Of course, the price came down since then a lot, and there's been a lot of activities going on. But again, the cost per test or cost per run reduced to some extent, but the cost of these machines hasn't changed massively. So when I was learning more about these methods and coming from electronic engineering and electrical engineering background, was thinking about why we're not measuring the electrical change of this reaction. Very simple idea. Of course, what they're teaching us in engineering school is like, I and V. I multiplied by V is power, so that's about energy, and I is the current over time. So like, and here we have a reaction. So definitely there should be some sort of a change of charge, and also there's some sort of a change of energy. So I brought that idea to head of Stanford Genome Technology Center, Professor Ron Davis, who's an amazing guy. So Ron has 4 bachelors: physics, math, biology, botany, PhD in biochemistry from Caltech, postdoc with Jim Watson, the Nobel laureate at Harvard, and was a Stanford professor from age of, 28, 29. Now I'm talking to him, he's 64 years old. And I'm telling him that, how about we using some sort of a macro sensors and and again, while he's not an engineer and he's not an electrical engineer, he walks the walk, he understands what I was referring to. And what I was explaining that we can use semiconductor technologies, he was very excited about the potential he can bring to the table. And then he started telling me that if he can really build that, that could be very revolutionary, that could be very game-changing, because we need genetic testing and reading this information for tons of different applications. Healthcare is only one of them, as the professor mentioned. So he convinced me I should work on it as my PhD project. I did so. I moved from radar to DNA. And while it looks so different, and there was a lot of interesting learning over the course of past decade, but there's a lot of similarities, believe it or not. Both of them is about signal to noise. Both of them you do detection. And both of them you do estimation, you do the signal processing. So you're defining a sensor, you're designing it, you're measuring the things. I mean, environment is different. Of course, here you're designing a chip that historically packaging of the chip is supposed to have no moisture around that. Here we're just injecting the moisture to the chip. So it required some special treatment, but that's engineering challenges, and this is fine. So that's how I started working at Stanford Genome Technology Center and chose a co-advisor also in the CIS building, which that's another story that we were working on, that lithography-related project. The first 2 years of my PhD, I was developing a quasi-electronic technology based on the, I explained to you that there's like charge that you can detect, or energy. So charge, there's multiple versions of this charge that you can detect. One of them is the proton or H plus ion that is get released of that reaction. So you can build an ion-sensitive field effect transistor, or ISFET, and having the DNA molecules right above that, and then the moment that this reaction happens that we just talked about, now the proton gets released right there. You can, that works like changing of the gate voltage. And then you can see that in the IV current voltage curve, and you can detect it over time. And you can do it for every single one of them over time, and since you know what you injected in, you can really read the DNA. So that was quite exciting. We've done similar things also for showing the energy detection. We call it thermosequencing because there's some sort of a thermal measurement. And that took 3-4 years here at Stanford. That was doing the different sort of a proof of concept of that one. But the majority of these two technologies were back in 2004, 2005. Soon we learned that even though that has some advantages, that now we can use a semiconductor chip and reduce the cost of this device from multi-$100,000 to probably 50 grand or 20 grand or such. Still, the workflow is the whole process of really getting these things. It's not as easy as what we like if you want to distribute this in a larger scale. The whole concept of PC in the world of mainframes for genomics. For instance, when you're trying to detect pH, one of the issues that you're running into, because of you detecting delta pH, you're detecting the release of proton ions, H plus ions, then your solution has to be in a very low buffer capacity. I don't know if you know what buffer capacity, what that means, like it's similar to the capacitors that we have, basically we have a high capacity versus low capacity. The same thing exists also for solutions. Solutions, they're adding some, additional materials there that basically doesn't allow big change of pH. And for majority of the bio-related work, that's how the biology works. They usually have stuff like tris and so on and so forth are in the solutions, keeping the capacity high. Now, if you wanted to detect the delta pH, you have to operate in an environment which actually has to be low pH. So to some extent, enzyme doesn't like it. There's some other challenges that you're running into. But there's actually another problem. If you have a low buffer capacity solution, the moment that it touches the air, the CO2 of the air can get dissolved here, and that CO2 get dissolved, create a big delta pH. So your signal, your noise is going to be way bigger than the signal you're trying to detect. So you have to really protect your liquid from any air. And for that purpose, you require a nitrogen tank or argon tank or so on and so forth to really use that. So that's one additional requirement. Also, the amount of data that you were collecting was less than images that historically people were collecting, but it still was more than what we could really just upload it to a cloud system and have it decentralized. Remember, we were trying to really figure out a way to make something which can be used for a really large scale with many people, not yet another like a Me Too version of things for the labs. So we start developing a new technology, which this time we call it the pure electronic or direct measurement. And that's really what we developed about 4 years at Stanford until late 2010. And then incorporated the company. I got my PhD, defended the PhD in December 2009. Wrote the thesis right after, incorporated the company in early 2010, licensed all of this work that you were talking about from OTL. That's a whole another subject that we can talk about probably for 6 hours. How to get that one and what type of goods and bads and uglies exist around, how to deal with OTL. And then we got a lot of government grants when we were developing the technology back at Stanford. Now I start writing some grants for the company. Given that we had the initial success, they start giving us money for the company, which was very helpful. So got some seed funding, incubator in Menlo Park, 700 square feet lab, 2 office upstairs, and then shared conference rooms and restrooms and the rest. And hired some consultants, brought some of the people working with me at Stanford. Fantastic SAB board, 10 Stanford prof, a couple of Harvard and MITs, Berkeley, Scripps, etc. We're trying to not discriminate. Still, we had like 10 times more from Stanford than other places. And then, that journey started now. It's been close to 7 years, 6.5 years. So we start building. At Stanford, we were working more of the core of the technology. It was more of a proof of concept detection. Since then, we start building. Okay, well now let's build the instrument. Let's build the chip. Let's build the multiple versions of instruments, from a breadboard to a prototype, to start changing the prototypes to an alpha machine and a beta machine and a commercial beta machine, etc. This is an extremely interdisciplinary project. It's probably the most interdisciplinary project you can imagine. We have in our company hardcore chip designers, analog, digital, working on hired from Apple and Intel and whatnot. We have people, surface chemists, we have molecular biologists, we have electrical engineers who are designing boards on the PCB level, we have microfluidic people, we have bioinformatics. There's a molecular biology, macrobiology, etc., etc. So there's a whole about 10 different disciplines needs to work together to make this technology to work. It's been a fascinating ride. To date, we brought in the development of the technology close to $100 million in. Half of that was from venture capitals in a seed round, Series A, Series B. The rest was non-dilutive capital in one way or the other. And then we have a great pent-up demand from the market. This is something that is quite exciting that people are interested to use. I'm going to give you a little bit more background about, in general, the use cases of these and why what we need really to enable in that front. Remember, I was talking about the pH detection story. That's the very first thing that we developed here. And we decided to put it aside and not using it. About 2 years later, back in 2007, end of 2007, 2008, one day I got a call from someone and then asking questions about that technology. And I was a PhD student like you guys. And I had no idea about how to talk to a businessman calling me from outside and asking a lot of detailed questions. And after 1 hour of detailed question, he told me, oh, by the way, I want to make sure that I'm not asking any confidential information. I said, oh, thanks for letting me know now at the end of the call. So long story short, there was one of the folks who were in this business and built a couple of companies in a related field, were very interested about that pH detection platform. Requested to license that from us, from Stanford. I was just the inventor. And finally, after 18 months of back and forth, he got a non-exclusive license on that platform. During this time, they started also building a prototype. Well, he had, again, given his previous experience, he also had money and other things, so he could move things forward. In June 2010, June 22nd, 2010, he finally, I think, got the license. About 45 days later, we got the news that that company called Ion Torrent got sold for $740 million to Life Technologies. And we're said, what exactly happened here? So Stanford did a okay deal. Probably they could do much better than what they've done, but that's not something that, it's impacted me financially, but that's not, except that is their business. The good news was that Ion Torrent ended up in hand of Life Technologies, which is the main company who did the Human Genome Project equipment development. A year and a half later, they commercialized that in 2011. And then in 2014, Life Technologies got sold to Thermo Fisher. That's one of the largest companies in this field for $15.6 billion. And there are rumors about what exactly the Ion Torrent piece valued, but it was a good portion. Today, that's the second largest platform that is offered as a DNA sequencing out there in the world. So majority of the market is in the hand of a company called Illumina. This is an optical-based platform that commercialized. They bought a company called Solexa, a startup company called Solexa in 2007, and then they commercialized it, and for the past 10 years they've been offering it. They have the range of hundreds of thousands of dollars to $10 million machine, own a major stake in the market. The second is the Ion Torrent platform. While, again, Stanford deal was an interesting one, it was for me, it was very fascinating to see that a project that we were working on, and we literally put it aside. We just said, like, this is not good enough for the purpose we're trying to achieve. Now is offering, and actually in oncology, that's a very, this is probably the most successful one, and is a commercially available product that you can go to, you can go to Thermo Fisher website and you can buy it, and many labs are using it, and worldwide. The reason I brought it up, trying to say that while we are students here and working on this idea or that idea, sometimes we don't realize the work that you're doing could be quite valuable, quite worthy of something. Not necessarily only from the financial standpoint, but also from the impact standpoint, from something that could be like a very valuable something that exists in the planet Earth. When I came to Stanford as an electrical engineer, we're thinking about, I studied signal processing, and I studied, and that's the only thing that I was considering to really work on. I was not really open to, exposed to other stuff except until I really started changing the major. And then, well, not the major, the field, the work that I was doing. But then I learned that actually what I learned in bachelor was, frankly, nothing. This is a basic science that you learn about, how you can get yourself exposed to something different. And in my opinion, electrical engineering is the best major in the world because of, both math and physics in a very practical, analytical way. So you can analyze almost everything that you like to have. So it gives us the opportunity to really tackle the problems which are not in the historical electrical engineering field and be very impactful. In fact, I think that the work that historically electrical engineers were doing are over. They did such a good job, we don't need that anymore. Back in days ago, Professor Tom Lee, which I believe he still is teaching, one day he came to a class and he said that in the next 5 years, every dog even gonna have a cell phone. So working on a cell phone wouldn't be as fancy as you think. So wireless communication went to a very, very high rise. But then after that, we have amazing solutions. And then if you want to spend your life of 5 years and developing specific things that are going to increase the efficiency of one of those algorithms, that maybe the voice behind the cell phone going to get 2.5% improved, it may not really reflect in the impact that you're looking for long run. Yes, you're going to get a PhD, don't worry about that. But except that, you have much more power to really implement if you're going to go out of the original field and trying to implement this knowledge and know-how in multidisciplinary and interdisciplinary areas. So with that, I'll pause for a moment and see if there's any question, if anything we wanted to talk about before I go to the next section, which is about Genapsys and the company. Awesome. So what we are trying to enable and what we're trying to achieve at Genapsys, we call it a molecular reader. Like one of the applications of the technology that we developed is DNA sequencing. But it's not only DNA sequencing. It's actually, you can use it for quite a range of other very small molecules like DNA, RNA, proteins, or even cells, single cell analysis. And it would be very impactful to have such a system, especially if it would be low cost. Cost matter at the end of the day a lot. I'm going to explain in a couple of slides why. It would be fast, would be accurate and easy to use. Ease of use is very important in my opinion. And at the end, it has to be portable. It has to be something that we can really have it wherever we need to have this technology. And the reason is we are living in the world of biology. And everything around us, majority of that, like a 95% plus, is actually biological stuff. We're made of 38 trillion cells in our body. We have more microbes in our gut than the cell in the body. The coffee that you drink, the tea, the food, this cotton, the leather, this wood, these are all like everything that you see around you. These are all like, they have molecular information. And today we are blind to it. We don't have an easy way to read that. But this is abundance level of extremely distributed information that is very critical. And these are impacting not only our healthcare, but tons of other applications. It's very critical to be able to read this information in a low-cost, easy-to-use, fast, and very distributed manner. That's something that needs to happen, like by Genapsys or by somebody else, but it has to happen. I have no doubt on that front. And this is something that, again, thinking about this feature set, we have been focusing on trying to see how we can enable. So you all know that DNA, we already talked about it, is the computer code of life, and really defining a lot of functions of everything around us. And cancer is the gene disease, or the change in the mutation. But if you wanted to look at some numbers, if you wanted to look at some statistics, some of these statistics are extremely interesting and scary, frankly. The chance of getting cancer during our lifetime, the first time I saw that, I freaked out, is more than 40%. More than 40%. So it means in this room right now, we are like 12 people, we have or 13 people right now sitting here. We're talking about at least 5 people are going to get cancer during our lifetime. If you're thinking about it, it's a little bit, serious number. It's not like 0.01% chance. It's a very high number. But the chances of success of a drug that has been built to diagnose cancer, to deal with cancer, is less than 10%. You spend 10 years, 8 to 10 years, $1 billion at the end, starting with 10,000 compound, going all the way to 1, clinical trial 1, clinical trial 2, clinical trial 3. If it works only for 30% of the population, you have to trash the drug. Because it's pretty much a lot of these is pretty much a blind studies. Like you just do these and you pass it through. Clinical trials are a version of really trying to test it in a little bit more meaningful way. Because we don't have an easy way to really look at these markers and find out if it works for 30%, what is specific about that 30%? If it works for 30%, let's get the drug out for that 30%. You save the drug, you save $1 billion, and now the solution is a much smaller solution. The problem is a much smaller problem. You need to only find a solution for the remaining 70%, and so on and so forth. It's called companion diagnostic. This field of really finding a way to get the drug out is called companion diagnostic. Pretty interesting field. And that's one area that is very important, how we can really deal with that. But application of genomics and DNA sequencing is way beyond healthcare. When we're talking about healthcare, there is prognostic. Prognostic means like super early diagnostic, early diagnostic. That is almost the best way to deal with something like cancer. Effective diagnostic, finding the treatment after you even figure out basically what's wrong with the person. Let's use the example of the cancer that we've been focusing on. Should we use chemotherapy A or chemotherapy B or surgery or radiotherapy? You cannot do all of them. You're going to kill the patient. So the question is that which one you want to really effectively implement. So finding the effective treatment. Then monitoring the treatment throughout the process. Finding out if the number of bad cells, the cancer cells, goes really down or not. Right now, we're just basically doing a surgery and doing chemotherapy on top of it and looking at the temperature and say, oh, do you feel well? And he or she will say that, yeah, I will do well. So, oh, that's good. And then 6 months later, 1 year later, 2 years later, you hear about remission. Because even some amount of those cancer cells left behind, then they start replicating and you're still in trouble. Or the cancer cells will start developing drug resistance after you start injecting these things, and then they don't respond anymore. And those little remaining ones are still quite problematic. So monitoring through the treatment. And of course, finding the effective drug, as we talked about, to really find out what is unique about these patients, what is about their gene marker. And has been numerous amount of clinical studies who's shown that actually with your gene marker, you can find out which drug might be more effective for you. There's a company actually in the neighborhood of Genapsys called Genomic Health, where the past 15 years they had, I don't know how many, but a lot of clinical trials and papers and whatnot. We've shown, for example, they started with the top 3 cancers. For example, for breast cancer, they've shown that in 80% of women with breast cancer, after surgery, they do not need radio. It doesn't make any difference for them with all of these studies to do radiotherapy or chemotherapy. But still, it's been advised by doctors and this is really bad, not only for the healthcare system, but also for the patient themselves. And this is really impacting the body. If you're taking radiotherapy once in your life for cancer A, then you cannot take it later on for cancer, another type. So it has a lot of downside as well. So all of these are in healthcare. But let's talk about some completely non-healthcare application. One of those would be agricultural biology. Today, we have more than 900 million people suffering from hunger around the globe. From UN and every place that are providing the data, the world population grows. By 2050, we're going to have about 10 billion. The hunger population from 900 million or about 1 billion going to get doubled. We used most of farmable lands. So it's not like we can go and really find new lands to just farm. The only way to feed the world is really to increase efficiency of every acre of the land. And I'm not talking about GMO. I'm talking about personalized farming. I'm talking about how we can increase efficiency, that we don't lose weight and fruit and whatever we're hoping to harvest at the end of summer. That is really happening. A couple of years ago in Florida and a couple of states next to it, there was this virus get to the citrus farms and $13 billion loss. That was a serious, because if they could catch it early when this disease outbreak is happening, similar to human disease outbreak that can happen to other stuff as well. If you could capture it early, you could really save a lot of those fruits and money and foods. So this is one of many applications that you want to really be able to do smart farming, personalized farming. Find out, okay, well, where you need to do what type of diseases it may get and whatnot. Other applications, food testing. You want to find out if the food is good or not, if it just went bad. Today, if the food is going bad in whatever, Costco and Safety, and how do they do that? They can't. They just make a decision. And it can cause people, it was reported 2015, 48 million people in US only got sick because of food-related poisoning, different type of food issues. That's a very serious number. And we don't have a solution, because if you wanted to take this sample and send it to a lab and get the results 4 months later, that just doesn't work. The food, the food is not going to even remain until then. We got one of these very large companies in the food industry reached out to us. They were saying that they have these trucks of food coming from Canada border, and then they wanted to find out the source and safety of the food. And they just can't today. And they were doing research and talking to some people. Actually, they reached out to folks at Harvard. I don't know why, not Stanford, but that person knew about us, so he's a SAB member. He connected basically them to us. So that's one of the other areas. Forensics, security, environmental. When I was back at Stanford, we were doing a project with Brazil, looking at corns to find out which one is a better biofuel. And so on and so forth. Right now, we have people who reached out. There's an oil company trying to look at the algae who are creating corrosion in the oil pipeline, and they wanted to really identify the type and be able to deal with that. There's a professor in Mexico making tequila. He's starting a company, and he wanted to really find out which one going to make a better tequila. There's so many applications. The number of applications are literally endless, and in multiple areas. Not only healthcare, but a lot of applied market. And of course, in top of all of this is research, is discovery, to better understand the biology, to better understand what's going on in the world. So with all of that, where we are standing today, we are still in a very early days. The total world population who's done any sort of genetic testing or genome sequenced is basically less than 0.005%. How many of us in this room have done genetic testing? Not 23andMe, which is a different story, but serious genetic testing to find out if you're getting any cancer or not. How many of us, our families, are doing that? And we are part of the privileged section of the society. So it's really early days. It's a lot of potential existing there. And a number of life science and molecular research labs, which they need these, there's about 400,000 of them. Only 3,000 can afford to have these massive big machines. So we think the problem is a mainframe to mobile transition, similar to what happened in the computer industry. In the left side, of course, in the top, you see the mainframe computers. It was prior to our days, and of course went to the PCs and to laptops and iPads and iPhones, and now your iPhone is much more powerful than old PCs. In the bottom left side, you see this. This is the most selling instrument out there. Costs about $1 million, with about $100-some thousand maintenance fee. 700 pound, 40 by 50 by 30 inches. As I mentioned, there are machines which cost $10 million, but this is a $1 million version of it. And that's, again, 700 pound requires a big server next to it and run in a very special condition. In the right side, this is our device, which is a footprint of an iPad. It's portable. Last class, a couple of years ago, when I gave a talk here, I brought it with myself. Today, I didn't because it was coming from somewhere else. But it's a little machine that you can carry it. It's pure semiconductor-based. There's no optics involved. There's no robots. There's all integrated. And the core of that technology is a semiconductor chip that they have some of those chips here. So you can have different number of sensors on that chip, but I use, for example, this one. And here you have millions of sensors right in the middle area here. And on top of that, this is like a 3-layer structure. So it's a sensor right in the middle. And then you have this plastic in top, which has a microfluidic channel. That's basically where the sample goes, and is sitting in top of all the sensors. And underneath, you have the LGA, which basically read the information from the chip. And that little machine supports this chip. And that machine is a self-standing machine. It doesn't need a computer. It already has a computer inside of it. It has a terabyte hard drive in it. It is wireless connected to the cloud. It's a pretty powerful machine from that standpoint, and it supports these. And this is the one who does all of the reading part, and the data coming off these one and goes to the cloud. And now if you have that, then you can do a lot of interesting work in all of those applications that we were talking about. Well, DNA sequencing market by itself, it seems to be a pretty amazing market. From the JP Morgan and UBS, it is a more than $20 billion market 2015, going to be less than 50 by 2018. That's assuming those big machines. A lot of people believe that if you can really shrink the size and make it easier to use and distribute it, it's going to be the next $100 billion technology business. In fact, actually, that article is about the work that I described earlier about the pH detection. That's the semiconductor machine wrote on that front. One of many applications is cancer. One of the many applications in cancer is early detection. This is a paper from PNAS, Proceeding of National Academy of Science, which probably after Nature and Science in the world of science is a really good place to publish. 2008, that shows basically the progress of cancer over time, starting from one cancer cell and start growing and making like a more and more number of that, go into the early carcinoma and advanced carcinoma, and then go to metastasis. And usually when it goes to metastasis, it's quite challenging to really fix. So it's very important that you be able to capture it early. Depends on the disease, but in general about the cancers, it takes about 30 years. I mean, there are cancers who are effective and literally kill someone in 2 weeks. But again, in overall, if you want to look at the average, it's a very long time. So it's super important if you can capture it early. I like the quote by Dr. Snyder, who is the head of a Stanford Genetic Department and director of Stanford Center for Genomics and Personalized Medicine. Disclosure, he's a SAB member of the company as well. He's talking about, if you look at the industrialized world, it's about 1 billion people. Of course, in China, we have more than 1 billion people. In India, we have more than 1 billion people. If you want to just do once a year annual checkup of a genetic testing at $100 a test, which is much more acceptable for insurances and people and everybody else to pay for that, versus today it doesn't exist and is a multi-$1,000. For 1 billion people, that's $100 billion recurring business every year. And that's really representing where we are with just starting this amazing field. So I stop here. If there's any question, happy to answer. But in general, I very much encourage our friends in the EE department to really use EE background in a lot of amazing fields that they need our expertise. Thank you very much.
We have time for one question.
They usually say that 9 out of 10 companies fail in their early stages of development, like in the startup period. I mean, my question is, what did you exactly do to make sure that you're the one who succeeds among all of those companies who did want to do the same thing as you wanted to do?
Thank you. That's a good question. I think I don't know the answer. What we did to make sure that's not the case. What I can guess is we were trying to be extremely clear with ourselves that we're not drinking our own Kool-Aid. We are really trying to get everything ready before we wanted to. Like, you need to basically crawl before you walk and walk before you run. A lot of these companies, I think, they're just getting super excited super early about, there's a $5 billion market about something, and I'm going to be $5 billion worth, which are not necessarily, there's not a causal relationship there, right? So I think the question is, do you have something which truly make a difference? You're the right person to do that, and can you take really the right steps to do that? As an example, back in 2006, when I was doing the management science degree, we wrote a business plan, specifically on DNA sequencing with a group of 4 other people. And at the end of that, the people who were giving grades to us, they were VCs. There's a very good course I recommend you guys, if you have the time to get it. I don't know if it's still as good as old days, but MSNE 273. It's called not venture formation, but something like that. MSNE 273 anyway. Back then, Steve Blank and a few others were teaching the course. Audrey McLean, etc. It was an amazing course. So at the end, the professors were not giving you the grade. They were getting VCs from Sand Hill Road coming and listening to you, and they were giving grades to you. So some of those folks were interested enough about what we're doing. We were, based on the business plan, we said, we want $5 million, and we want to build 1 working sensor in the scale, in the small scale. And one of them said, I'm interested to invest here. So, and definitely I got very excited, and I thought that, okay, well, that's the time to go and start a company. Went and told OTL, Office of Technology Licensing, and they said, okay, well, I want to license these, and so on and so forth. Then I went to my advisor, my PhD advisor, and I told him, there's great opportunity. We can start these. And and he told me that we just got an NIH grant, a 5 years NIH grant, a $1 million NIH grant. And he told me, like, why? Why you wanted to go under the pressure of VCs while we already have the money to really develop it in-house, and this is early, so let's just de-risk it here in school. And of course, yes, there were risks. For example, there was a company who got a license from us and got sold for $740 million. But put that aside, that was a great advice, in my opinion. So from 2006, 2007, until we really started the company, that was 3-4 years later. But we got much more data points that we knew this is working now to a much higher confidence level. Again, this is a very interdisciplinary, complex, field. But that helped a lot. And then, and we were trying to take the very same approach as we were going forward. In my Series A, for example, there was a lot of investors who were trying to give you more money than what we wanted. We thought that we want to raise 20 million, but there were some investors who were trying to give us 50. And we're trying to really push back and said, hey, why 50? Oh, you probably need it. So, okay, well, yes, we may need it, but we're going to come back. Why we need to get it today from you? And then when I saw that dynamic, then I even asked the people that, you know what, I said 20, but actually I don't want 20. I want only 10. Because there are apparently interested parties, so why should I raise all 20 now? And then I chose the party who was willing to work with me on a lower amount, and the second one would be in my hand to decide if I want to raise that money or not. So really being able to have a lot of again, baby steps and control the steps, I think that helps. I was an elementary school teacher. After I got my bachelor, I got my high school diploma in math and physics. In Iran, you select, even in high school, if you wanted to study math and physics versus biology versus art. Then I went to Tehran, the capital city. I got a bachelor in electrical engineering from Sharif University of Technology. If you're an electrical engineer here, I'm sure you probably met some other people from Sharif University as well. Then right after that, I did a dual degree in petroleum engineering, which was just a random thing. And then I came to Stanford, getting my master's, both in EE and 2 years later in MSNE, management science, and got my PhD in electrical engineering. The last year of PhD, I went to med school. It seemed that I really liked the school, but I never finished that. I started a company, Genapsys, and that's really the 3 areas and 3 places that I've been over the past 15 years. I have 3 brothers, no sister. All 3 of my brothers, actually, they did very similar story. They got their master PhD also here at EE at Stanford. One of them, the youngest one, is a postdoc right now here. You probably see him around. The second youngest, which is on the left side, he's working for KLA Tanker. He did his PhD with Marty Fayer in Kingston Lab. And Rahim worked, he's now an engineering research associate at Stanford as well. So he got his master PhD postdoc here as well. So from that standpoint, we've always been around. We've been here at Stanford, and you may see them as the student here. In my past life, I was working, in fact, who are contributing a lot, like one of the Stanford EE professors, one of the nicest people that I've ever met when I was at school, got diagnosed with cancer at a very young age. So these type of diseases are really hunting us down, impacting our lives, and we don't really know what's going on. And it was very disturbing to really deal with that concept. Why medicine is still so behind? Why medicine is still in the cave age? So I started learning more about genomics and DNA sequencing. And when you dig in, basically in the world of biology, the highest resolution things that you have is like molecules. nucleic acids, which is DNA, RNA. Then from RNAs, you're creating proteins. Proteins are the one who's defining the function of the cell. And then you have cells, which is like, a bunch of cells creating organs and the rest of these as our body. So majority of these diseases having some sort of genomic cause or a genetic relevance. Different type of cancers. Cancer is DNA disease. Cancer is when the DNA is like, ATCGs is not happening in the right place. Majority of the time in the DNA, but also RNA. We have the same thing also in the protein level. So these are molecules, and these molecules are really teeny tiny. A DNA molecule, like we have about 38 trillion cells in our body. Each cell has DNA. DNA, the whole DNA of a human for each cell is 6.4 billion base pair, ATCGs. And so it's a lot of information. And we all started from one cell, like in a fetus. And that started replicating 1 to 2, 2 to 4, 4 to 16, and so on and so forth. And now we are 38 trillion cells. And every moment of time, we have like, billions of new cells that is really happening. This process, like any other process in the world, is not perfect. So there are errors. Well, thank you very much. I appreciate the introduction. Happy to be back at Stanford. I practically never left. I'm going to tell a little bit more about my story. So I've been always involved in one way or the other with a lot of Stanford-related activities. Today, I thought that first I give maybe a quick background about myself and what I did and where I'm coming from, and then talk a bit more about Genapsys and what you're doing there, and open it up to any question that may exist. Making sure that this is good. So at Genapsys, the motto is digitize the world. We're going to come back to it. What's the relevance to digitize the world? Why digitize the world if it's a DNA sequencing company? I'm coming, I was born and raised in Iran, a country in Middle East. Iran and Iraq are neighbors, even though some people couldn't really make a distinction between the two, but they're two different countries. In Iran, I was born in a city called Sirjan, in middle south of Iran. It's a little town with 150,000 people. And the historically is a few thousand years old town or city. The main business of people over there either is pistachio farms or is like a beautiful Persian rocks called kilim or gelim. I was born in a middle-class family. Both of my parents are teachers. My dad was teaching science in middle school, and my mom was happening in the process of replication of one cell to two cell. So you have this DNA in the double helix, as you know, is get single-stranded, and the second strand get built up. This process with an enzyme that is trying to really build the second DNA, the first enzyme error is 10 to the minus 7. There's a second enzyme coming trying to clean some errors up, and that's about 10 to the minus 2. So if everything works really perfectly, then you have about 10 to the minus 9 error rate, and of course you have 6.4 10 to the 9 bases, so you get about maybe 6 of them wrong, and depends on where that happens, you might be in a okay shape, and basically life continues, or you're in trouble. And of course, as we grow, this number of, if you have an error here and another error there, this is higher chance of you getting to a problem. And that's why with age, we increase the chance of getting diseases like cancers and whatnot. Of course, we can inherit these things from our parents, or it can happen during our lifetime. DNA molecule, each base, ATCGs, are less than a nanometer apart. Of course, it's a 3D structure. So they're really small molecules. With the ATCGs, you want to read them. DNA sequencing is the method of reading that code. that like, what is the code basically associated to this one. When I was trying to dig into these, I realized that, okay, well, reading that DNA and RNA code is a very important part of understanding majority of these diseases. The methods that existed for these are mainly optical technologies. So the way that they do it is that, and that's both for optical technologies and other technologies, is called, most of them is called sequencing, but working on completely different stuff. I was working on radars and signal processing, hardcore signal processing, wireless communication related stuff. Actually, I was part of the wireless network lab in the 3rd floor of Packard building, which was Ahmed Bahai and Andre Goldsmith lab. And there was a very interesting project using a multi-antenna radar imaging system, using multi-antennas UWB ultra-wideband to see the signal behind the wall. I was interested in healthcare for very personal reason. A family member of mine, close family member of mine, was misdiagnosed at really young age of 15. And it was very disturbing to watch how broken medicine is. I mean, when coming to semiconductor and when coming to nanotechnology, we're pretty advanced. I mean, these gadgets, the phones that we have is really a miracle. I said before that if Steve Jobs claimed to be a prophet, I was in his religion. This is really amazing what electrical engineers have achieved over the past 2-3 decades. We can move atoms. We can write IBM with 18 atoms. But if it goes to medicine, we are still in a cave age. You get different type of weird diseases, and just telling you that, hey, you have like cancer. I mean, wait, what? It was not supposed to be. In fact, a dear friend of mine has a cousin who the cousin is a serial entrepreneur, very successful, PhD from Carnegie Mellon, computer science, 35 years old. And 2 months ago, 35 years old, 2 months ago got diagnosed with a stage 3 brain tumor. And it's not even the type that you can operate. It's just quite, separated. Basically, it's a thin layer on top of brain. And, imagine that you're like 30 or 35 years old or so on and so forth, and then just telling you that you're stage 3 and you have like a few months to live. We know that great people